Okay, I'd like to introduce Maya Fishback, Dr. Maya Fishback. She's the assistant professor at the Canadian Institute for Theoretical Astrophysics at the University of Toronto. Before moving to Toronto, she was a NASA Einstein Postdoctoral Fellow at Northwestern University. She earned her PhD in astronomy and astrophysics at the University of Chicago in 2020. Dr. Fishback started her PhD studies in the same month as the first direct detection of gravitational waves in September of 2015. That's 10 years ago. This exciting discovery motivated Dr. Fishback to enter the emerging field of gravitational wave astrophysics. Dr. Fishback's research, she listens to those gravitational waves in order to piece together what they're teaching us about our universe.
I'm Maya Fishback, and today I'll be talking about what we can learn about black holes and also neutron stars with gravitational waves, and I'll explain what all these things are. So just to start off, this movie is actually almost exactly 10 years old at this point. This is a simulation of the system that we directly detected in gravitational waves for the first time in September of 2015. So here we have two black holes that are orbiting around each other. And as they're doing so, they're radiating energy and angular momentum in gravitational waves that causes them to come closer and closer together. And then eventually they merge and make one final black hole at the end. And so for the rest of the talk, I'll be explaining those different pieces of what gravitational waves are, what black holes are, and then also what those things can teach us. So black holes, in case anyone isn't familiar, are the densest objects in the universe. So here is actually the very first picture of a black hole that was taken by the Event Horizon Telescope collaboration a few years ago. And so what you see here, it looks very blurry, but it's actually a very, very high resolution photograph. And so the thing in the middle is the black hole, and then the light around here is essentially the light that's directly outside of the event horizon of a black hole. So black holes are so dense that they don't emit any light from inside the event horizon. Basically, the gravity of a black hole is so strong that if you are standing within this surface called the event horizon and you shine a flashlight, the light from your flashlight will just fall back into the black hole. So nothing can escape, not even light. Light is the messenger that moves the fastest in the universe. So if light can't escape, that means that anything else that you try to throw out of the black hole also wouldn't make it out. Everything is just going to fall back in to the center of the black hole. And so that's briefly what a black hole is. It's just something that is extremely dense that not even light can escape. So for example, if you took the Earth and managed to squeeze it down so that it was less than a centimeter in radius, that would also turn into a black hole. So anything can be a black hole as long as it is dense enough. And later I will talk more about exactly the types of black holes that we're observing with gravitational waves. But just to explain what gravitational waves are, this goes back to Einstein's theory of gravity, which he formulated for the first time in 1915, over 100 years ago. And the idea behind this theory of gravity is that space and time are linked. So three-dimensional space and one-dimensional time make up this four-dimensional surface. And this, you can think about this as a fabric that describes our entire universe. And the analogy is that masses that are in that fabric, so anything any matter in the universe will respond according to the curvature of this fabric of space-time. So space-time tells matter how to move, and matter tells space-time how to curve. Is this quote by John Wheeler, a famous relativist, that explains this idea where you basically have anything that has mass, so like the Earth and the Moon, is going to create this curvature, these valleys in space-time. And then if you have a little marble right on this fabric, it's going to fall down into those valleys. And so gravity is not a force that is pulling the moon to the Earth, for example. Gravity is just how we describe this curving, this geometry of space-time. And so it's just that the moon is that the things around the Earth will feel this this curvature and like will roll down that valley. And so this matter and space-time are linked in this way, like having objects on a fabric. And gravitational waves enter the image I showed you before was kind of the static image of just masses resting on a fabric. But gravitational waves are how information is carried about the curvature of space-time to distant points in the space. So when massive objects move, they cause these ripples in the space-time. And another analogy I like to think about this is if you imagine a pond and a water bug that is on the surface of that pond. So the water bug is like a massive object that is moving on the pond of space-time, and that water bug is going to create these ripples that then are spread out from that source and can reach distant parts of that pond and essentially send the message to distant parts of space-time that a massive object has moved, perhaps the curvature it has changed. So that's how, so gravitational waves are these ripples in space-time, these information carriers about the motions of massive objects. And so here is basically the same movie I showed in the beginning, but now a different representation of those two black holes that are orbiting around each other, where now there's this space-time. You can see behind it this fabric, and here's a visualization of those ripples, those gravitational waves that are propagating out from those black holes, because those black holes are massive objects that are moving, like that water bug on the pond. And now these ripples travel out to distant corners of the universe, traveling for billions of years until they reach us here on Earth, for example. And so the effect of this gravitational wave, so now imagine that gravitational wave was carried out and has arrived billions of years later on Earth, is to stretch and squeeze matter. And so it's going to actually deform space in this way and to deform matter in this way. Of course, the movie that we see here is highly exaggerated. The Earth doesn't really turn to jello. Here's the movie again. And yeah, it's a very exaggerated effect, because in reality, gravitational waves are extremely weak. You can think about this as the fabric of space-time is extremely stiff, so it's actually very difficult to create large ripples in space-time. A loud gravitational wave, and so the loudest gravitational waves are the things we've been able to detect so far, so things involving big black holes, for example. Those are only changing the distance between our sun and the next closest star, which is more than 4 light years away by the width of a human hair. So in order to detect gravitational waves, we have to probe these fractional changes in distance, these deformations in space-time that are less than 1 width of a human hair per 4 light years, right? So it's tiny, tiny relative changes in distance. And so that means that in order to detect gravitational waves, we need not only a loud source of gravitational waves, but also a really, really precise detector. And I'm going to be explaining both of these things, but to start off, I'll talk about the really precise detector. And so again, to go over the physical effect of gravitational waves, which will explain how we're detecting them, is we're looking for an effect that is going to be visualized in this movie that I will soon play, where essentially you can imagine that I have a ring of test masses, so a ring of test masses here, and now an entire array of rings of test masses, one behind each other. And now I'm going to send a gravitational wave through this tube. And so the gravitational wave is traveling through this tube. And as it hits each ring of test masses, it's going to cause that ring to stretch and squeeze in this pattern that you see here. So the points further away from each other on that ring are going to move more than points close together. And the gravitational wave will travel through this tube of test masses. In reality, they travel at the speed of light. So obviously this is slowed down for the movie. But that is essentially the effect that we're trying to measure. This is the physical effect on gravitational waves on this imaginary ring of test masses, is this pattern of stretching and squeezing. And so here's just one slice of that. So one ring of test masses that's being stretched and squeezed as a gravitational wave is passing through the screen. And the way that LIGO works, the Laser Interferometer Gravitational Wave Observatory, that's what LIGO stands for, is instead of having a whole ring of test masses, we just have 2 test masses that are 90 degrees orthogonal to each other. And these test masses are mirrors at the end of these 2 big tunnels. So we have these 2 arms, these 2 tunnels, each one 4 kilometers long. So this is much bigger than, a normal telescope. It's 4 kilometers by 4 kilometers. And we have these mirrors at the end. And when a gravitational wave passes overhead or beneath the detector, then it causes these test masses to move in this pattern. One arm gets a little bit longer and the other one gets a little bit shorter. And we measure that change in distance with laser light. So light always travels at the same speed. And so we can measure if one arm gets a little bit longer relative to the other arm by measuring the light travel time down each arm. So as a gravitational wave passes through, the arms should change length in this pattern relative to each other. And that is going to be reflected in the laser light that we recover. And so let me just show another movie that explains how this works. And so here, these are the 2 mirrors, those 2, I said, test masses that are at the end of each of those 4 kilometer arms. And now we're shooting a laser down each arm. And as a gravitational wave passes and those arms change length relative to each other, the light is actually a wave, right? And so that wave is going to travel down each arm and then recombine over here. And now that recombining is either destructive interference, so the waves cancel each other out, but as the arms move relative to each other, it becomes constructive interference and the waves actually add. And so that causes this flashing pattern at the output where you can see that the arms have moved relative to each other because of this pattern of destructive and constructive interference of the waves, which are the laser light. And so that is how we use lasers to measure these changes in distance, the stretching and squeezing that is due to gravitational waves. I mentioned that earlier that gravitational waves are extremely, extremely weak. And so the relative changes in distance that we're measuring are really, really tiny fractions in terms of physical units. So we have these 4-kilometer arms, and the amount that those arms are actually getting longer and shorter when a loud gravitational wave passes is a tiny, tiny fraction of an atomic nucleus. And so we need to be able to measure changes in distance that are much, much smaller than an atomic nucleus, which is very, seems like a very challenging thing to do. And it's amazing that we actually have the technology to be able to do that and have done it at this point hundreds of times with hundreds of gravitational wave events. So that was about how the detector works. The detector, just to explain this analogy in the slide here, the detector is really like this microphone. It's not like a regular astronomical telescope, that you have to point to the source you're trying to see. It really is like a microphone that picks up gravitational waves, is just listening for gravitational waves from across the universe. And so it's broadly sensitive to gravitational waves anywhere above or below the detector. If you're trying to hit the side of the detector, it's less sensitive. But it has this really broad sensitivity for each detector. And the loud source of gravitational waves are like this speaker, right, that the detector is trying to listen for. And so let me explain a bit about the sources of gravitational waves. And so I've mentioned this a few times already, but the main source of gravitational waves that we've detected are merging black holes. So this was the movie I showed at the very beginning, right? We have 2 black holes. In this case, each black hole is 30 times the mass of the sun. They're orbiting around each other. Actually, at this point, they're moving close to the speed of light, so as fast as they possibly can. They're really massive, really dense things moving super quickly, and eventually they merge. And the fact that we're dealing with such gravitationally extreme objects moving at very high speeds is what makes these extremely loud sources of gravitational waves. So the type of gravitational wave that is emitted from these merging black holes has this distinct morphology, which is partially why we're able to detect them, and then also how we're able to learn about the sources from the gravitational waves that we're observing. And so the idea is that we have these 2 black holes here. They're orbiting around each other or spiraling around each other. And the first stage of that is called the in-spiral stage. And so down here, you see the strength of the gravitational wave as a function of time. So the amplitude of the wave, which tells you how loud it is, how much stretching and squeezing it's going to do. So larger values here are going to be more stretching and squeezing that the wave is doing. And then time is moving this way. And so at this in-spiral stage, the gravitational wave frequency is twice the orbital frequency. So if those black holes are moving around each other more slowly, then the gravitational wave will correspondingly be stretched out. And so as they're getting closer and closer together, the gravitational wave frequency is increasing as the orbital frequency increases. The black holes are completing an orbit faster. And so the frequency of the gravitational waves also increases, and it also gets louder as the black holes come closer together, as they're moving faster and the gravitational field is more extreme. So you have, during the in-spiral stage, you have the frequency and the amplitude of the gravitational wave increasing. And then eventually those two black holes get so close together that their event horizons touch, and they're essentially at this merger stage. That's where you get this peak in the gravitational wave amplitude. And then you just have this one deformed black hole that is ringing down, much like a bell that's been struck. And so it's vibrating. And this ring down phase, you can see here, it's kind of becomes damped out as the final black hole is shedding off any imperfections. And then it settles down into a final black hole that is no longer emitting any gravitational waves, so the system goes quiet. And that's because the final black hole, even though it is very gravitationally extreme, it's no longer moving. And so you need extreme densities, extreme masses that are moving very quickly in order to make a loud gravitational wave. And by moving, we mean moving in a non-spherically symmetric way. So that final black hole is just perfectly symmetric. It's no longer emitting gravitational waves, and that's when things go quiet. And so this is the characteristic signal that we look for if we're trying to find merging black holes in our gravitational wave data. And this has a very distinct morphology, but it also is, the gravitational wave signal is a little bit different. For example, if we have more massive black holes, the frequency of the gravitational waves is lower. If the black holes are each rotating in some way, that is also going to affect this frequency evolution. If the mass ratios of the black holes, like if one black hole is much bigger than the other, that's also going to affect this exact frequency evolution. But this is the general picture. And I'm not sure you'll be able to hear any audio, but you can kind of see it here, right, that as we go through time, the frequency of the gravitational wave and the amplitude increases. And so that ends up sounding like if you put this signal in the audio band, which is close to the band that it's in, where the frequencies we're talking about for these black holes that we're detecting are around 100 hertz. And so that actually is the human hearing band, which is another aspect of why we use the listening analogy. But it'll sound like a chirp. It'll go from low frequency to high frequency, like whoop. So that's what these signals sound like. And you can see that here. Again, not sure any of you can actually hear what I'm hearing right now. But anyway, this is the real gravitational wave data from that first event. You can see we have two LIGO detectors, so two different L-shaped detectors, one in Hanford in Washington State and one in Livingston, Louisiana. And this is the data. Down here is the waves that they saw. This is this waveform from before on top of detector noise. Let me just wait for this to play again. So this is that waveform. It's harder to see on top of the noise here. And then these chirps that you see up here, we call these chirps. This is a time frequency representation of that signal. And so this is in each bin here, the brightness of that pixel is how much power there is at that time and frequency band. So at early times, there's a lot of power at these lower frequencies in both detectors. And then at later times, you can see this distinct swoosh up to having a lot of power at high frequencies. And so this is this chirp that we're listening for to know that two black holes have merged somewhere in the universe. And so I kind of showed the data from these two LIGO detectors in Hanford and Livingston. It's really important for us to have multiple gravitational wave detectors because these are really, really quiet signals that we're trying to detect on top of the noise. And as you can imagine, what we're trying to measure are the mirrors of the two arms changing distance relative to each other. So kind of moving relative to each other by tiny, tiny distances smaller than an atomic nucleus. And so by having multiple detectors, we're able to rule out that the mirrors moving is something that's local, that's because like the ground is shaking under the detector or something, right? It's there's a lot of environmental disturbances that we try really hard to isolate, but having the exact same signal in two detectors gives us confidence that the signal is actually coming from outer space. It's something in the universe that's creating gravitational waves rather than just some noise here on Earth. Having more than two detectors really helps us localize and know where in the sky this source is coming from. And so in addition to the two LIGOs, we have the Virgo detector in Italy, LIGO India, which is a third LIGO detector that will be in India that is going to come online soon. The construction has already started, and the Kagra detector in Japan. And so we have these multiple gravitational wave detectors. Each one is very similar. It's this interferometer, this L shape. And by having these multiple detectors, we can essentially triangulate based on the time of arrival of the gravitational wave signal in each detector. We can then pinpoint roughly the area in the sky that it came from. Because again, with just one detector, we have very broad sensitivity. So all we can say is there was a gravitational wave that was probably somewhere overhead this detector on the sky or underneath it. And so that is really good for having broad sensitivity to a huge fraction of the sky, but it's really bad if you want to know where in the sky the black hole merger happened. Okay, and so with this network of detectors, in addition to that very first event, which was two black holes, roughly 30 times the mass of the sun that merged with each other, we have almost 100 gravitational wave events from similar systems that we have published to date as the LIGO Virgo Kagra collaboration. And there are actually double that amount. So or we have, we're doubling this catalog, so we have around 100 new events that we're going to publish in just a couple of weeks from now. So stay tuned for that. August 23rd, we have a big data release with a lot of exciting events in there. And also, we've been collecting data for the past few years. By the end of our current observing run, we'll have a few hundred of these events. So that's extremely exciting to go from no gravitational wave detections 10 years ago to 300 10 years later. And so all of these, so here, right, I'm showing that chirp representation, that time frequency, like distinct swoosh that you can see for each one of these events in reality. So we do the analysis on the waveform, measure the frequencies and the frequency evolution to figure out, for example, the masses of the black holes involved. And so here's a visualization of that where you can see the variety of, this isn't all of the events, but you can, see some of them are some of those black holes, let me play this again, are really big. And so they're moving relatively slowly, whereas some of these guys are much smaller, and so they're orbiting around each other very quickly. And so that kind of gives you a sense of the variety of black holes and some neutron stars that we have observed. Here's another visualization that I really like to show where these gravitational waves are in mass space. So basically, for each time we detect a gravitational wave signal that is really two black holes or neutron stars, so two of these compact objects that then merge and make a bigger one. And so each one of these arrow system here represents a gravitational wave event where the ordering in the horizontal space doesn't mean anything, but on the vertical scale, this shows the masses. So how heavy those black holes are. The in blue are all the black holes we've seen in gravitational waves. And so you can just see that we've seen black holes as small as around 5 times the mass of the sun. And if you consider the merger products, we've seen things that are almost 200 times the mass of the sun. We just had an announcement last month with the biggest ever gravitational wave merger of black hole that we've detected to date, and that involved 2 black holes that were each over 100 times the mass of the sun. That made a final black hole that's almost 300 solar masses. So here you can see some of that diversity and how heavy the black holes are. Down here in orange are some neutron stars that we've also discovered, which I'll talk about next. And then for comparison are the neutron stars in yellow and black holes in red that we've known about before gravitational waves with traditional astronomical probes. So if you've heard of pulsars or X-ray binaries, these are the sorts of systems that we could detect just from electromagnetic emission. But with gravitational waves, we have so many more of these black holes and a growing number of neutron stars that we're able to add to the catalog. And so one reason why I'm really excited about all of these black holes that we're observing with gravitational waves is that they are able to probe the rarest, most massive stars in the universe. And so really massive stars, so stars that are over 10 times the mass of the sun, even up to a few hundred times the mass of the sun at the end of their lives. So they explode in a core collapse supernova, and they make a black hole. And so these stars are really important because they shine brighter than than their less massive companions. So they shine really, really brightly, and they have a really huge effect on like shaping their entire host galaxies, but they live for a really short amount of time. And so it's very difficult to observe them while they're alive, but they make these black holes that then go on and just exist essentially forever. And so by observing all of these black holes, we're able to piece together their prehistories and learn about the massive stars that gave rise to them in a really unique way. And so one of the questions that we're trying to answer is exactly how these black holes, especially in these binary systems, the black holes that merge with other black holes, exactly how that system was made, and what their progenitor stars were like, what kinds of environments did they live in. And so a few of my collaborators have coined this phrase gravitational wave paleontology to describe this field of study where we essentially learn about the stars from the black hole skeletons they leave behind in the stellar graveyard. And so I love giving talks about black hole skeletons on Halloween because it's very spooky. But it also really is like we're doing paleontology and just taking these black hole fossils and trying to reconstruct the evolutionary histories of the stars that came before them and a lot of uncertain stellar physics, binary interactions, supernova, so the deaths of the stars, and trying to learn about all those physical processes by just looking at what are the properties of the black holes that are left behind. How heavy are they? How, are they rotating? How fast are they rotating? What kind of galaxies are they in? And things like that. Okay, so I did also want to say a few words about neutron stars because I think black holes are super awesome, but neutron stars are arguably even more exciting because they're still very extreme. They're less dense than black holes, but still denser than anything we can imagine. And unlike black holes, they're not dark. So they are essentially very extreme matter. So there's still stuff in there that's just pushed to extreme density. So a neutron star is essentially like a giant atomic nucleus made up of neutrons and protons that is just more than the mass of the sun squished into something that is just a handful of kilometers across. So very extreme. And so far we've detected one merger involving two neutron stars that we also detected light from. And so I'll just show this movie, which shows that merger of those two neutron stars, and then essentially this remarkable display of cosmic fireworks that ensued and across the electromagnetic spectrum. So from gamma rays, the most energetic form of light, to radio waves, which are very long wavelength, and everything in between, in the optical and infrared and X-rays, basically everything. We detected so much from this one source. I won't explain it in detail because I'm running out of time, but feel free to ask me more about that. That detection happened in 2017. So you may have heard about it at the time. One thing that is really exciting about merging neutron stars is that we think these are a primary, or at least a very significant site for making some of the heaviest metals that we have in our periodic table and in our universe. And so this shows the periodic table, so from chemistry, right? And the different astrophysical sources of the different elements. And so the merging neutron stars are colored in yellow with what fraction of that, the abundance of that heavy element do we think is made in merging neutron stars. And so very popular elements like gold and platinum. Merging neutron stars are a primary source for producing those things. You're essentially just merging a lot of very nuclear rich material, so a lot of neutrons with each other, and that's a great way to build up to heavier atomic nuclei. And so that one event that we saw in 2017 made hundreds of Earth masses of gold and platinum, for example, which is pretty cool. Of course, we can't get rich off of it because it was hundreds of millions of light years away. So can't quite get there and harvest that gold and platinum. But we don't do astronomy to get rich, I guess. So the other sorts of science questions that we can address with gravitational waves are gravitational wave cosmology. And so one thing that's really unique about gravitational waves is that the gravitational wave signal itself gives us a direct measure of the distance to the source. So they are great cosmic rulers because we don't need any kind of calibration. When we see a gravitational wave signal, we know the distance to that source, which is really, really rare in astronomy because, normally when you see a galaxy, you don't know, like, is that just a very bright galaxy that's far away, or is it a faint galaxy that's closer by? There's usually this degeneracy between how bright something is and how far away it is. But with gravitational waves, we don't have that degeneracy. We get the intrinsic brightness of the gravitational wave from the frequency evolution, and then the brightness that we measure in our detector tells us the distance. And so that allows us to do things like measure the Hubble relation, the speed versus distance, which tells us about cosmology, what our universe is made out of, and things like how old the universe is, what its age is. And so happy to also talk more about that during the questions. And just to conclude, there's a lot we can learn from gravitational waves, a lot we've started to learn about in the first 10 years of gravitational wave astronomy, and a very bright future ahead. So to summarize what I talked about, gravitational waves carry information about the motion of massive objects. The loudest sources of gravitational waves are collisions of black holes and neutron stars, and we can detect these gravitational waves with these interferometers like LIGO, Virgo, and COGRA. By analyzing the gravitational waves, we can measure the properties of those black holes and neutron stars, like the masses, spins, distance, and sky locations. And with a catalog, so our current catalog is around 100 of merging black holes and neutron stars, and we have a few hundred more we're still analyzing. By putting all these signals together, we can learn about stars, the origin of heavy elements, the age of the universe, a bunch of other stuff, and also make unexpected discoveries. So with that, I am happy to take any questions.
Maya, thank you so much. That was great and very understandable for a complicated area that has a lot of math and other things associated with it. Katie, I believe you had your hand up first. Katie Good.
Her mic.
You have to unmute. If you want to ask a question, just do a hand raise and then we'll get in the queue for it. Richard, hi, are you on? Okay. Oh, Katie's back.
Yes,
okay, Richard, go ahead.
Yes, I wrote my question on the chat, but I'll just summarize it succinctly. So you were mentioning how like black holes are considered the most massive objects in the universe. So I was considering something that could be, have a bigger effect of producing gravitational waves. And so the thought that I had was the Big Bang that created the universe. So I was just curious, like, what's your thoughts of like the theoretical event of the Big Bang causing such a massive gravitational waves from the beginning, I guess in a way like primordial gravitational waves that could potentially still be detected, or could potentially our galaxy, right, or the Milky Way could still be, quote unquote, like riding one of those original gravitational waves that originated from the Big Bang.
Yeah, that's a really good point. So basically, so the Big Bang, we're almost sure, if the Big Bang happened, it would have made gravitational waves that should be detectable, but not at the frequencies that we're sensitive to with our Earth-based detectors. So the reason I've been focusing on these merging black holes and neutron stars, also in this specific mass range, so things that are a few to tens to hundreds times the mass of the sun, is because they make loud gravitational waves at the frequencies that we can detect them with this particular technology, which is around tens to 1,000 hertz. So the Big Bang and like inflation produced gravitational waves at much, much lower frequencies. And this is something that people are searching for, the imprints of those low frequency gravitational waves in the cosmic microwave background. And basically this relic, this earliest light that we can probe. So that last scattering surface is that the furthest back we can see is this primordial radiation from the time, well, as long as we can see after the Big Bang, which is still a few 100,000 years. But basically those gravitational waves would be imprinted in patterns of the fluctuations that we can see on that map, the cosmic microwave background map. And so it's the exact same physics of the theory of gravity and the gravitational waves, but it is a different source and a different frequency. And so gravitational waves, so yeah, I guess I've been focusing here on the one source of gravitational waves that we've detected so far, which are these black holes and neutron stars, but there are probably so many sources of gravitational waves at so many frequencies, right? And so it's like, even though when we first started pointing electromagnetic telescopes that look for light from the sky, anyway, sorry, I should probably move on to any other questions, but yeah, that's a great point. And there are tons of sources of gravitational waves out there. We just are at the beginning of what we're able to detect.
Okay.
Thank you, Mike.
Jeffrey Kretsch, you're next.
Oh, you say Jeff Kretsch? Okay.
Yeah.
Yeah, I had a question. I know the effect at this distance from the event is like a human hair over, say, 4 light years, this and that. How big is it within the galaxy where this occurred? Does it get to a point where it's physically a fact that it lived within a few light years of that, for example? Would that be centimeters over, say, the size of a planet? Or
That's a really good question. So essentially the scaling of that gravitational wave is proportional to distance, or inversely proportional to distance. So yeah, if you are 1,000,000 times closer to the source of the gravitational wave, then the effect will be 1,000,000 times stronger. That is still really, really tiny, because we're essentially, it's 1 part in 10 to the 21. So even if you are 1,000,000 times closer, you're still 1 part in 10 to the 15. So it is really, really hard to make a loud gravitational wave unless you are like in it's, yeah, I mean, basically you would have to get close enough that the effect of the gravitational wave is not the main, like at that point you are, so close to a black hole that you feel directly the gravity of the black hole, rather than the gravitational wave, I think. But yeah, there are some cool like back of the envelopes thing you could definitely play around with there.
So this wouldn't wipe out the civilizations in that galaxy. Yeah. Okay.
Yeah.
George, you're next.
Yes, I have a question. If I understand you correctly, you can have these black holes can have different masses, and you can measure the differences in the mass, I suppose, by the shapes of the profiles and how these shapes evolve with time. Is that correct?
Yes.
When I looked at the first black hole thing where you have the measure, there's a lot of noise on those waves. There must be errors in this. So how big are the errors roughly for doing this? Because I know it's on the profiles, they're not real smooth wave profiles.
Yes, yeah, definitely. Yeah, that's a really great point. So we definitely do have errors on all of our measurements. There are some combinations of masses, for example, that are better measured than others. So, for example, this combination known as the chirp mass is the thing that is really driving the chirp. And so that combination, which is related to the total mass and the mass ratio of the two black holes, that we can typically measure to a few percent level. But the mass ratio is much harder to measure. So typically we will say like, oh, we observed two black holes, one of which was probably between 28 and 35 times the mass of the sun, and the other one was between 10 and 15 or something like that. So we do have these few solar mass uncertainties on our measurements. Some events which are much louder than others, then those are the ones where the power in the signal is much bigger than the noise. They have a higher signal to noise ratio. And so we get really good measurements on those. And then the quieter ones, we have much higher error bars. And these are the things that, we do a lot of data analysis to figure out exactly what the error bars are and how we can combine multiple events to get something to essentially reduce the errors and things like that. So yeah, we think a lot about those uncertainties. So thanks for bringing that up.
Okay. John Birch, did you get your connection working to where you want to ask a question?
Well, I'm having trouble with the video, but the audio seems to be okay. Can you hear me?
Yeah, just fine.
Okay, I'll ask the ones that are directly related to the LIGO. Could it be possible to have a LIGO at the Lagrange points?
Yes. So you mean like in space?
Yes, because you have a much larger length of, you have a much bigger lens, if you will.
Yeah. So so these are, I've talked about like our LIGO Virgo Cogra detector network. There are other gravitational wave detector concepts at various levels of maturity. The most mature one, which is similar, is also an interferometer, is LISA, the Laser Interferometer Space Antenna. And so that is due to launch in around 10 years from now. That will be that is a space-based detector. So it's essentially 3 spacecrafts that are communicating to each other by lasers, shooting lasers back and forth, and are able to detect will be able to detect gravitational waves once it's launched and in orbit that are because it's on a much bigger scale, it's able to detect things at much lower frequencies. And so LISA will detect collisions of black holes that are millions of times the mass of the sun compared to tens of times the mass of the sun. And so these are the sorts of black holes that are in the centers of galaxies, for example, and a whole bunch of other gravitational wave sources that will be at those lower frequencies than what we can detect here on Earth.
Okay, and I also wanted to ask, in what ways do gravity waves behave differently from electromagnetic waves? Because it seems like you're talking about the ring down. That it seems like that has to be from the SR of the black hole, the merged black holes, the Schwarzschild radius.
Yeah.
And that shouldn't the rate of time there be virtually standstill?
Yeah, it does. Yeah, these sorts of things in relativity do kind of, they're very mind bending in a lot of ways. But yes, essentially, the main difference, I would say the main difference practically between gravitational waves and electromagnetic waves is that gravitational waves are so weakly interacting with other stuff that this is also what makes them so useful. They're very clean messengers. They respond to gravity and not much else. Whereas if you have light that's being emitted from some very extreme, very dense source, it'll take it a while to like make it out and get to our telescopes. And it also, gets all messed up. There's like all this interference. And so it's not as clean of a messenger as gravitational waves, where we can like really look at the signal and see what we're looking at. As far as how do the gravitational waves make it out of the event horizon, it really is I guess in that way, the gravitational waves are also different from light. They're not really coming out of the black hole. It really is the geometry of the black hole,
the nearby space,
coupling with space-time, that is creating the gravitational waves, if that makes sense.
So it's the nearby space that's being plucked, if you will. So that the gravity wave is actually emitting from the surrounding space rather than from within or the surface, from the Schwarzschild radius.
Yeah, exactly. It's coming from the surface, but not like inside the surface.
Okay,
Yeah.
Richard, we have the last question. Richard High has one, and we'll be wrapping up for the evening.
Yeah, thanks. I was just kind of like looking at what you have in your slide and regarding the unexpected discoveries. So I was just curious, what do you hope to discover with these technologies that we have?
So I guess different people will say different things, but I think the discovery potential is really enormous. So there are other types of sources that I didn't talk about other than black holes and neutron stars that we are searching for. But I think so. These are things like the gravitational waves from a supernova. So when a star actually explodes, that's a lot of dense material moving very quickly. That could produce gravitational waves. Things like rotating neutron stars, if there's some tiny like millimeter high hill on top of a neutron star, that produces gravitational waves. And then there's just so much that we probably haven't thought of because we've been studying the night sky with electromagnetic radiation, with light for millennia, and we've only just opened this gravitational wave window. So centuries ago, we probably wouldn't have expected that, black holes exist in our universe. And so I think there's a whole bunch of stuff like that we could discover with gravitational waves that we just haven't even thought about yet.
Awesome. Thank
Maya,
you.
thank you so much. I think everyone's really enjoyed it. And if you're ever in the Washington, D.C. area and is around one of our meetings or events, we would love to have you come and visit us in person.
Yeah, thank you so much. This was really fun. Thanks for all the really great questions.
Okay. Well, folks, we'll see you next month. And thank you for attending. And thank you again, Maya. This will end the meeting.